All right, this is Honors Algebra 2 Pre-Calc. We're doing 5.3 in Algebra 2, which is still factoring, but now we're going to focus on factoring two specific kinds of things, perfect square trinomials, or PSTs, and factoring by grouping, which we've done a little bit of already. So the caveat I'm going to give you about perfect square trinomials is if you really don't remember these, it's not going to be the worst thing in the world, but they are kind of handy to know. So what it means to be a perfect square trinomial is that it's the same binomial squared. Like, for instance, x plus 3 quantity squared. If you FOIL that out, you end up with x squared plus 2 times 3x, which would be a 6x, plus 9. Or x minus 3 quantity squared, which if you FOIL it out, you'd get an x squared minus 2 times that 3x plus 9. So essentially, these patterns, right, if something is a perfect square, meaning it is a binomial that would be squared and would FOIL out into a perfect square trinomial, what it's going to look like is either a squared plus 2ab plus b squared, or a squared minus 2ab plus b squared. Notice that if you do a squared plus 2ab plus b squared, it's an a plus b, and if you have an a squared minus 2ab plus b squared, it's an a minus b quantity squared. You don't have to notice this. You could just factor these the same way that we've factored all of the other examples, and you'd be fine, but it's a lot nicer in terms of speed if you can notice this. So let's walk through. Here are the things that you're looking for if something's a perfect square trinomial, and you can see it here and here, right, or here and here, wherever you want to look, right? So if something is a perfect square trinomial, right, what's going to happen is you're going to have a perfect square as the first term, you're going to have a square as the last term, and then in the middle, right, so this would be like an a squared, and that's like a b squared, right? And then in the middle, what's going to happen is you're going to have double of whatever a times b is, right? So and it could be a plus or minus depending on whether it's a plus, right, or a minus inside the parentheses. So let's look at what we're looking at here. Now you can factor this the old school way. You could say, oh, I get it. My front seats have to be an x and an x. My back seats are either a 1 and a 36, or a 2 and an 18, or a 3 and a 12, or a 4 and a 9, or a 6 and a 6. But they have to add to 12x. Oh, hey, look, it's a 6 and a 6, and you would get that this is x plus 6 times x plus 6. Or you could write that as x plus 6 quantity squared. There's nothing wrong with having to do that the old school way, with having to like actually straight up factor it however you choose. But if you notice that x squared plus 12x plus 36, if you notice, oh, hey, this is a perfect square, it's x times x, and this is a perfect square, it's 6 times 6, and this guy right here is conveniently double of this product, right? It's 2 times the x times the 6, it's double of that, right? Or 2 times 6x. Then you can say, oh, okay, cool, this is an x and a 6, I keep the sign, the whole thing squared, right? And that's fine. You can spot it or you can not spot it, it really doesn't matter to me. There are lots of people that go through really long math careers doing lots and lots of math and never can spot a perfect square trinomial, and that's fine. Doesn't matter. If we look at the second one, right, again, the hint that it's a perfect square trinomial is that this is a perfect square, right? It's x squared. This is a perfect square. It's 5 squared. And this is double of those two numbers, right? 2 times 5 times x, and it's got a minus sign. So this is going to be an x minus 5 quantity squared. Now, if you had to go through that the longer way, right? If you had to go through both of these the long way instead of spotting the perfect square trinomial pattern, it's fine, right? Not a big deal. When we do completing the square, which will be 5.4, that's our next section, you'll see that it is helpful sometimes to spot a perfect square trinomial, but again, you don't really have to, it's fine. All right, let's go ahead and do a P8. All right, so same idea. You can either factor this the old school way, or you can spot that this is a perfect square trinomial. Either way, I'd suggest that you pause me and try the problem by yourself. So I'm going to go ahead and do it now, assuming that you have taken me off pause. So this is a perfect square, and this is a perfect square. So perfect square of x, perfect square of 10, right? And sure enough, this is double that product, right? So this is a perfect square trinomial, and I keep this plus sign, so I get x plus 10 quantity squared. Or if you like it better, you can write it as x plus 10 times x plus 10. Doesn't matter, right? Up to you. And again, if you don't spot this, then you can just go through factoring the way that we've gone through all of our other factoring, and there's nothing wrong with it. Same thing here, right? Perfect square of x, perfect square of 9, and sure enough, this is double a 9x, right? So I keep the sign, and I get that this is an x minus 9 quantity squared. Or you could write it as an x minus 9 times an x minus 9. right? But that's basically the gist of perfect square trinomials. All right, let's keep moving forward. So let's talk about factoring by grouping. So grouping is useful if you have an even number of terms, 1, 2, 3, 4, right? 1, 2, 3, 4. And conveniently, I have identical coefficient ratios. And I'll explain to you what I mean by this in a sec, but the problem is that I can't give you a problem yet that doesn't work by grouping because you don't know synthetic division. So once I teach you synthetic division, then I can show you problems where grouping doesn't work. But for right now, grouping's kind of got to work. So here's what I mean by the coefficient ratio. See how this coefficient ratio is an 8 to a negative 16, and see how this coefficient ratio is a 3 to a negative 6? Both of those are a ratio of 1 to negative 2, right? If you simplify them, they're both a ratio of 1 to negative 2. That means grouping is going to work. But again, for right now, I don't have much choice. I have to give you something where grouping works. So let's talk about what grouping is. Grouping is sort of like if you go to a party, right? So let's say your friend invites you to a party. You're going to go to this party with your friend, and you're super stoked, and it's great, and you show up, and then you get a text from your friend who totally just bailed on you. And you walk into this party because at this point, you know, no Ubers are around, you've got nowhere else to go. We're assuming that this is a party after everyone's done being quarantined for the pandemic. But anyway, don't go out partying during the pandemic, please. Anyway. So you're at this party and you suddenly don't have a friend and you don't want to leave because you don't have any other plans for the night and you have no good way to get home right now. So you're like, all right, cool, I guess I'll just chill. And you walk in and probably the first thing you do is you try to find somebody in the room that you have something in common with. Or maybe you try to find a corner to hang out all by yourself and you're just going to screw around on your phone and that's your choice. But let's pretend for the argument of this grouping thing that you find someone you have anything in common with. You look at the person standing next to the chips and you're like, oh, I like chips too. And you stand next to that person because now you can talk about chips. Or you look at the person wearing an Eagles hat and you're like, yo, I love the Eagles too. And you stand next to them. So that's kind of what factoring by grouping is like. If you look at this whole thing, there is no GCF. These guys are all in a party and they have nothing in common, right? They walk in, all four of these people walk in and think, man, why am I even here? So then they awkwardly cling to the person next to them. These two say, oh, let's hang, I'm sure we can find something in common, and these two do the same thing. So we're going to find a group GCF in each of these groups, right? So in this first group, I could take out an 8x squared, and if I did that, I'd be left with an x minus 2, right? And in the second group, if I also said, hey, these folks right here, they have something in common, so I take out the 3, and I'm left with an x minus 2, right? So I took out a group GCF from both of them. And what ends up happening is we find this underlying commonality. I can factor out the x minus 2, and what's left is the 8x squared plus 3. So 8x squared plus 3, and now we're fully factored. Okay, so that's factoring by grouping. It's very similar to what you do when you do product sum method factoring a quadratic trinomial. Essentially, when you use product sum method on a quadratic trinomial, keep in mind that it is a trinomial because it has 3 terms, but when you use those magic number methods of product sum, you essentially split the middle term into 2 pieces, thus making it 4 terms, which means it has an even number of terms and you can group it, right? That's really what product sum method is. It's turning a trinomial into a quadrinomial so that you can factor by grouping. All right, so let's go ahead and walk through B. So when I try and do B, let's see what we've got in common. So notice there's no GCF of the whole thing, but I can group these first 2 folks together and these back 2 folks together and try and take out a group GCF. Well, the 5x cubed and the 3x squared only have an x squared in common, and I'm left with a 5x plus 3, right? Now I'm hoping to factor something out of the negative 20x minus 12 to also get a 5x plus 3. Sure enough, if I take out a negative 4, I get a 5x plus 3. So now I have this new group GCF, right? Like this new big GCF in parentheses that I can take out. And what seems to be left is an x squared minus 4. But this is a tricky question because while this one right here was prime, this one right here is a difference of squares, right? We covered that in a previous video. This still factors, right? So this is going to stay as a 5x plus 3. But since this guy's actually an x squared minus a 2 squared, he's going to factor into x plus 2, x minus 2. And that's my fully factored form, okay? All right, so I'm going to give you a P9 to try. All right, so as always, you can pause me if you want, but I'm going to go ahead and walk through P9. Again, pause me if you want to do it by yourself. So I'm going to go ahead and I see it's 4 terms. I see there's no GCF, so I'm going to group the first 2 and the last 2. So my ratio is essentially a 2 to negative 4, or which is the same as a 1 to negative 2, and you'll see that that's the same ratio here. So I take out my GCF of a 2x squared from the first group, and I'm left with an x minus 2. And I take out my GCF of a 7 from the back pair, and I'm left with an x minus 2. So now this x minus 2 is my new GCF. I pull out an x minus 2, I'm left with a 2x squared plus 7, which is prime, so I am factored, right? Over here, right, again, I'm going to see if I can find this group GCF and this group GCF. So when I look at these, I see that they have a 4x squared in common, and what seems to be left is a 3x plus 1. And here I can take out a negative 1 and also end up with that same value in the parentheses, that 3x plus 1. So this 3x plus 1 is my new GCF. Right, that's my new GCF, and what's left is a 4x squared minus 1, but I'm not done because that's a difference of squares, right? This is actually a 2x quantity squared minus a 1 squared, so that's going to factor into a 2x plus 1 and a 2x minus 1. And now I have a fully factored expression, and that's it.